In order to be able to discuss SN1 reactions, we first have to be able to understand a little bit more about carbocations, which are the intermediates in such reactions. And in this lesson, we're going to talk about the stability of carbocations. Carbocations in general are highly unstable species. Okay, they only have 6 electrons around the central carbon. The carbon's only forming 3 bonds, and there's an empty orbital. None of which are things that are particularly happy for an organic molecule. What we have to consider then is what factors stabilize them enough so that they can be intermediates in the SN1 reaction. Some carbocations are so unstable that for all intents and purposes they don't exist. Their energy is so high that there's no way you could ever climb that energy barrier to be able to access them and have them participate in the SN1 reaction. So the first factor contributing to carbocation stability is increased alkyl substitution. So a tertiary carbocation is more stable than a secondary, which is much, much more stable than a primary, and that's still more stable than the methyl carbocation. Why? Well, let's look at a somewhat realistic picture of the tertiary carbocation. So carbocations are planar, at least with respect to the carbon that has the positive charge on it, but then in a tertiary carbocation, each of the 3 carbons bound to the carbon with the positive charge has tetrahedral geometry. In the simplest tertiary carbocation, such as the tert-butyl carbocation, there are 3 hydrogens on each of those carbons. So there are 9 what we call beta carbon-hydrogen bonds. And what happens is that the carbocation is so hungry for electrons that it looks around and says, where can I grab electrons from? And what it finds are the electrons in these, what we call beta carbon-hydrogen bonds. So it reaches out to one of them over here and says, hey, beta carbon-hydrogen bond, can I have some of your electrons, please? And the beta carbon-hydrogen bond, of course, doesn't want to give its electrons to the carbocation, but they're still kind of come in and see what's going on, okay? They're attracted to the positive charge. In a tertiary carbocation, there are 9 such beta carbon-hydrogen bonds. So even though the positive charge never succeeds at taking those electrons from any one beta carbon-hydrogen bond, it has a lot of different options to choose from in its attempt to go grab electrons. So we could say that that positive charge is busy looking for electrons in lots of different places and negotiating, so to speak, with the different beta carbon-hydrogen bonds so that it is stable enough to exist for the time scale that you need to be an intermediate in an SN1 reaction. Okay, what about other types of carbocations? Well, in a secondary, there are only 6 of those beta carbon-hydrogen bonds. So the positively charged carbon doesn't have as much to keep itself busy. So it gets bored and starts to think, oh my God, I am so depressed. I don't have enough electrons. Maybe I should just self-destruct. It doesn't get quite that bad with a secondary in most cases because it still has some ability to keep itself busy, but it is clearly less occupied and has time to sit around and mope. That's going to increase its instability further, and under normal conditions, a secondary carbocation will not be stable enough to be an intermediate in most SN1 reactions. With primary, it gets even worse. Okay, there's only 3 beta carbon-hydrogen bonds, so that carbocation's positive charge spends most of its time moping and can only occasionally be thinking about trying to steal electrons from a nearby bond. And the methyl is the absolute worst case. There are no beta carbon-hydrogen bonds. So the methyl can't spend any time looking for electrons in such bonds because such bonds do not exist. Therefore, the methyl really, really, really is too unstable to exist. So in general, as I said, only the tertiary carbocations are stable enough by this mechanism of alkyl substitution to be intermediates in an SN1 reaction. The second factor that contributes to the stability of carbocations is resonance. So in general, the more resonance structures you can draw for a carbocation, or for any organic structure for that matter, the more stable that structure is. But especially in the case of the carbocation, the more resonance structures you have, the better, because when you have multiple resonance structures, that positive charge is shared among multiple different atoms. Sometimes they're carbon, and sometimes, as we'll see, they could be oxygen. Therefore, no single carbon has to bear a full positive charge. And this helps quite a bit. So in a previous lesson on resonance, you have already been introduced to the three important examples of resonance-stabilized carbocations, but I will go over them once again here for the sake of refreshing your memory. The first one being the allylic carbocation, in which the positive charge is on the carbon next to, but not directly on a double bond. And you see how there are two resonance structures for the allylic carbocation. Then there's the benzylic carbocation, in which the positive charge is on the carbon next to, but not directly on a benzene ring. So there are a total of 4 resonance structures for the benzylic carbocation. And then finally, we have the oxocarbocation, where the positive charge is on a carbon next to an oxygen atom, and we have 2 resonance structures for the oxocarbocation. This particular stabilized carbocation is especially good because all atoms are obeying the octet rule. Remember that the oxygen, even though it has a positive charge, it still has 8 electrons around it. So in this second major resonance structure, there are no atoms that have only 6 electrons around it. In the allylic and benzylic, while you're sharing the positive charge, there is always an atom that has only 6 electrons around it. So how much of an effect does resonance have? Well, in general, a secondary with resonance is as stable as a tertiary, and a primary with resonance is as stable as a secondary. So if you have resonance, even if it's secondary, you can get into the SN1 game fairly easily.